Good day to all of you students. Now we'll proceed with the part two of our discussion about the fundamentals of electricity and electronics. In the previous meeting we discussed all about the type of electric circuits. So we know that there are two types of these things, the series circuits and the parallel circuit. Then what these series circuits are? Well, series circuits consist of several devices, each of them linked up one after another in just a single large loop. Let's relate this in reality. If we have series lights, since it's Christmas now, then that's one example of a series connection because bulbs in a series lights, as we call it, are connected from the endpoint of the other one to the endpoint of the other. Okay? Though different devices have different voltages across them, the same current flows every device in a series circuit. If any one of the devices in a series circuit is broken, the whole circuit fails. So that's the advantage of having a series circuit. For instance, if two light bulbs are linked up in parallel and one is unscrewed, the other one will work. Modern Christmas tree lights are done in parallel circuits so that even if a single light burns out, the whole strand doesn't have to be thrown up. So, actually, guys, in the current situation that we have, series lights are now in parallel connection. That's why one bulb fails, then the other bulb still functions. Okay, so that's one thing about the series lights. Again, there are two types of electric circuits. We have the series circuits and the parallel circuits. Okay, in parallel circuits, different devices are arranged so that a single source supplies voltage to a separate loops of wire. The voltage in every device across the circuit is exactly the same, but in general, different devices are going to see different currents. Okay, in parallel circuit, the voltage are the same, but in parallel also, the current may differ from one another. In this case, each device is going to work even if the other ones fail. For instance, if two light bulbs are linked up in parallel and one is unscrewed, the other one will work. Modern Christmas tree lights are done in parallel circuits so that even if a single light burns out, the whole strand doesn't have to be thrown out. Okay? Now, let's proceed to one of the most important things to learn about the fundamentals of electricity and electronics. Okay, we have Ohm's law examples here. So in Ohm's law, just imagine this pyramid here. We have the voltage, we have the current, and resistance. Okay, so the formula we have E is equal. Let's just say V is equals to IR. Okay, so since its V is equal to IR, V is directly proportional to the current times resistance. Okay. But on the other hand, when you want to find out the current of a circuit, then it goes like I is equal to V over R. So current is now inversion directly, how you call that? Let's just say another example. So let's just see another example here. Like I need more like whiteboard maybe later on. We'll discuss it further. So Ohm's law is a formula used to calculate the relationship between voltage, current, and resistance in an electrical circuit. To students of electronics, Ohm's law E is equals to IR, but we use the V is equal to IR, is as fundamentally important as Einstein theory of relativity equation, which is E is equals to mc squared. It is to physicists. Is equal to I times R. When spelled out, it means voltage is equal to current times resistance. Again, voltage is equals to current times resistance. If you want to find the voltage, we can also say it as volts is equals to amps times ohms, or V is equal to A times the symbol of ohms. Named for German physicist George Ohm, 1789 to 1854. Ohm's law addresses the key quantities at work in circuits. Again, if you want to find the voltage, you need to multiply the given current and resistance of the circuit. Okay? Ohm's law. For Ohm's law, voltage in this example, voltage is letter E, current is I, and R, and resistance is R. Okay, you just have to remember that the unit of measure for voltage is V, unit of measure for current is A or ampere or amp, unit of measure for resistance is ohm or this symbol here. Role in circuits. For voltage, pressure that triggers electron flow. For current, rate of electron flow. And resistance is the flow inhibitor. Okay? Now, in case you're wondering, E is equal to electromotive force. So that's the old school term of the voltage. That's electromotive force. That's why they use the letter E. Well, the I is the intensity. That's why they use the I for the current, and for the symbol of the resistance, it's actually a Greek letter omega. Now for the Ohm's law, as I've said earlier, if you want to like find the voltage, so the formula would be E is equals to time I times R. So you can see here on this pyramid. So E is equals to I times R. But if you want to get the resistance, which is the I, it becomes I here. Then as you can see, E over R. So that's current is equals to voltage over resistance. So we have now a division of values. Now on the other side also, if you want to find the resistance or the R, here it should be voltage over current. So just as easy as that to remember the Ohm's law that we have. Ohm's law example, as you can see here. So we have here the resistance is 6 ohms, the voltage is 12 volts. Now, what would be the current for the circuit? Now, we'll go back to the previous example. If we're going to look for the I here, so we have to use I is equal to E over R. That's I is equal to 12 over 6. Okay? So now, 12 over 6 is what? So that's 2. So the answer here is 2 amperes. Okay? So we have the current here 2 amperes. Now, let's proceed. We just have, I think we need to use the whiteboard for this example here. Okay? So I can explain it to you that well. So let's share this tab first. So on the previous example, um, what's missing was I, right? So let's just use this pen. So I, so that's the current. That's why it was question mark. Okay. Now we have the value of the resistance. Resistance is equal to 6 ohms, right? And then the value of E, which is the voltage, is equal to 12 volts. Now, since we have this given, we use the formula I is equal to E over R, right? So since we have I is equal to E over R, then I is equal to 6 over 12. sorry. I mean 12 over 6. So what is 12 over 6? So now I becomes 2 ampere. So that's the answer for that circuit. So this is the answer. Okay? Did you get it now? Okay, so let's go back to the presentation. Okay, since we now find how to calculate this one, then we'll proceed to the R. So as you can see here, the formula for the calculation of resistance is E over I. So we have here E of 24 volts divided by 6. So what is 24 divided by 6? Okay? So that is 4. If we calculate it, just we can do it mentally, but to make sure, let's try to calculate using our calculator. 24 divided by 6. So our resistance here is 4 ohms. Okay? Now, E is what we're looking for here. So the formula would be E is equal to I times R. You just have to multiply the resistance and the amperes. Now, 5 amperes times 8 ohms is equal to 5 times 8 is equals to 40. That's 40 volts. Okay? So we have 40 volts in this circuit. Okay? Let's talk about energy and power. In physics, energy is defined as the amount of work that can be performed by force, whereas power is defined as the rate at which work is performed. Now let's see this comparison here. Well, energy, as with the definition, energy is the capacity to do work. Energy is power integrated over time, while power is the rate at which work is done or energy is transmitted. Well, the unit for energy is joules, which is equal to watt seconds, or joule is equal to Newton meter. So, and then for power, it's watt, joules per second. Okay? The symbol for energy is W and the power is P. Now, example, I left a 60-watt light bulb on for 30 days, which raised my electric bill by 43.2 kilowatt hours. The next one is my car's battery can provide 500 amps at 12 volts, which is equal to 6 kilowatt of power. Let's go to the different forms of power and energy. There are different forms of energy. These include kinetic, potential, thermal, gravitational, electromagnetic, sound, light, and elastic. So there, as you can see here, there are different forms of energy. The form of energy is dependent on the frame of reference and can be transformed into other forms. For instance, potential energy is dependent on the position of the object, whereas kinetic energy is the energy required to accelerate an object to a particular speed, and so on. Different forms of power could be electric power, which is the rate at which electrical energy is transferred by a circuit, human power, and optical power. Power is an energy per unit of time as a rate of change work done, or the energy of a subsystem power is equal to work over time. So we have here P is equal to W over T, where P is power, W is work, and T is time. What is power? Power, clearly power? No, power is the rate of using or supplying energy. As we have known, Power is equal to energy over time. Power is measured in watts, energy is measured in joules, and time is measured in seconds. That's why the unit for power, we have joules per second. Okay? Calculating power using current and voltage. Now, there are three ways of writing an equation for power, current, and voltage. So the general equation that we have is power is equal to current times voltage. Okay? The three ways are P is equal to current times voltage as we have here, or we have also I is equals to PV and V is equals to PI. So that either of these three that will be missing and two are given, then we can calculate the missing one. Okay? Again, where P power in watts, V voltage in volts, I current in amps, A or power in P or power in milliwatts, V voltage in volts, current in milliamps. The PIV triangle. You can use the PIV triangle to help you remember these three equations. Use it in the same way as Ohm's law triangle. Okay? To calculate power, put your finger over P. This leaves IV. Okay? So the equation is P is equals to I times V. To calculate the current, I put your finger I. This leaves P over V. So the equation is I is equals to PV. You just have to remember what we have done for the Ohm's law here. Imagine this is a triangle here. This is a triangle, then we divide it here and we divide it here. So you can actually get the formula now. The amp is quite large for electronics, so we often measure current in milliamps and power in milliwatts. So 1 milliampere is equal to 0.001 ampere, and 1 milliwatt is equal to 0.001 watts. Now, calculating power using resistance. Using Ohm's law, we have V is equals to I times R. We can convert P is equal to 1 times V to P is equals to I squared times R. So that is the square of the current times the resistance. And P is equals to the square of voltage over the resistance. So take note of this formula. Maybe we can use it in the near future for your reference as well. Where P power in watts, W I current in amps, R resistance in ohms, and V voltage in volts. The triangles, again, just like the pyramid form we have for the Ohm's law. You can use triangles to help with these equations too. So that's why we just have to divide this and know what we are going to do with this. Now, energy wasted power and overheating. Normally, electric power is useful, making a lamp, light, or a motor turn, for example. However, electrical energy is converted to heat. So that's the common thing about conversion of the energy that we have used. That's why when we light up our bulbs, when we touch it after lighting, so it's hot because electrical energy is was then converted into heat. Okay? Whenever a current flows through a resistance, and this can be a problem if it makes a device or wire overheat. And in electronics, the effect is usually negligible. But if the resistance is low, a wire or low value resistor, for example, the current can be sufficiently large to cause a problem. You can see from the equation P is equal to I squared times R that for a given resistance, the power depends on the current squared. So doubling the current will give 4 times the power. Resistors are rated by maximum power. They can have developed in them without damage. But power ratings are rarely quoted in parts list because the standard ratings of 0.25 watts or zero point 0.5 watts are suitable for most circuits. Further information is available on the resistors page. Wires and cables are rated by the maximum current they can pass without overheating. So that's why we choose, we have numbers for wire. So that's actually the thickness of the wire because it affects the heating of the wires, especially when we use high current devices. Like for me, our microwave oven heats fast. That's why when after using the microwave oven, you can feel the wire that it's heating. They have a very low resistance so that the maximum current is relatively large. For further information about current, please see cable page. Excuse me. Energy and power. Energy, the amount of energy used or supply depends on the power at the time for which it is used. We have seen this earlier. Energy is equal to power times time. A low power device operating for a low time can use more energy than a high power device, okay, for a short time. A low, for example, a 60-watt lamp switch on for 8 hours uses 60 watts times 8 times 3,600. So if we try to calculate this, why we using 36,000? Okay. Now, um, the formula, that's why we have 60 times 60, we have 3,600 because in 1 hour we have 3,600 seconds. Okay, then it was used for 8 hours. That's why we have the value 1728 kilojoules. A 3 kilowatt kettle switched on for 5 minutes uses 3,000 watts times 5 times 60 seconds is equal to 900 kilojoules. Excuse me for a while now. Now, the standard unit for energy is the joule, but 1 joule is a very small amount of energy for mains electricity. So kilojoule or megajoule are sometimes used in scientific work. In the home, we measure electrical energy in kilowatt hours. That's why in our electric bills, it is indicated the amount of kilowatt hours we use for the entire month. Often just called a unit of electricity when the context is clear. 1 kilowatt hour is the energy used by a 1 kilowatt power appliance when it is switched on for 1 hour. Okay, we have 1 kilowatt hour is equal to 1 kilowatt times 1 hour. A 60 watt lamp switch on for 8 hours uses a 0.06 kilowatt times 8. That's 4 That's 0.48 kilowatt hour. Okay, a 3 kilowatt kettle switch on for 5 minutes uses 3 kilowatt times 5 over 60. That's why 5 over 60, because we only used 5 minutes out of 60 minutes in 1 hour. That's why we have 0.25 kilowatt hour. Okay? Excuse me. You may need to convert the kilowatt domestic unit to scientific energy unit, the joule. So 1 kilowatt hour is equal to 1 kilowatt times 1 hour. So that's why it's 1 kilowatt hour is equal to 1,000 watts. The value 1 kilowatt times 3,600. That's for one. That's for six. That's for 1 hour. That's 3.6 megajoules. Power supply characteristics. Any power supply ideally must have the following characteristics. The magnitude of the output must be presented accurately and precisely. Second, the ripple content of the output must be zero. The output voltage must have high stability irrespective of load currents and line voltage changes. Fourth, the source impedance must be zero. It should be portable. So we have here the sources of DC voltage. The following is the list of DC voltage sources and shows the application of the types of source. Primary cells, secondary cells, alkaline batteries, nickel cadmium cells, lithium sulfur dioxide, lithium iodine cells, DC voltage standard, the laboratory power supply, line operated power, uninterrupted power supplies. So these are its application. For the power supply, the commonly used power supply with electronic circuits is the line operated power supply. In this, the mains voltage is utilized in a transformer or directly to work a rectifier. The rectified output will be filtered using a filter circuit that eliminates the ripple of the content of the rectified output. The output of the power supply will be pulsating an unidirectional current. The block diagram of the power supply is shown in figure. Main output, we have a transformer, rectifier, filter, bleeder, and until it has its DC output. That's all for the part two of our electricity and electronics topic. And I hope to see you on our next topic, which will be the motors and gears. Okay? So we will have these topics along the way. See you soon. Thank you. God bless.